And so defrost happens when, you have the outdoor coil that's grabbing all this heat in, and now we have this frost buildup that you can see on the right-hand side. And this was an actual tested unit that happened at 39 degrees outside, about 80% relative humidity because it was raining. So if I were to guess, that happens quite often in the winter months in the Washington area. So fairly mild temperatures, you get some rain. This could happen, and you need the refrigerant cycle to run in reverse. That basically says, instead of grabbing heat out of the outdoor air, let's discharge it from the compressor, that hot gas, and reject it at this condenser coil now in cooling mode so that we can melt those frost conditions. And in those situations, you need secondary heat or some sort of recirculation so that you can prevent cold air delivering directly to the space. In the testing that we did, we found that whatever was entering that indoor coil, if you were in a defrost cycle, you left that coil about 10 degrees cooler. So in this example, if I was entering at 39 degrees, I would be discharging about 29 degrees off that coil in defrost. That's where you need to size that secondary heat source. Couple other points: the highest frost risk on rainy and snowy days is between 32 and 45 degrees ambient. And this is exactly why we're seeing frost conditions in this 39-degree day. When you're below 32, the surface of the outdoor coil is, liquid precipitation freezes upon contact with the coil surface, right? So it's not going to necessarily freeze the coil. Precipitation is dry snow below 32 degrees. So the snow is less likely to stick on the coil if you're overall below that 32 degrees. And then above 45, you're not necessarily worried about it because the coil surface is not freezing. So that 32 to 45 degrees is that sweet spot where that surface is below freezing, but then you have moisture that's going to freeze on that coil.